So let's continue. We talked about kinematic design, and we started with basic 2D or planar cases, and then continued to spatial domain or in 3D space. But many times there are certain issues. So there are, of course, some benefits, but at the same time, there are certain limitations, and we have to be aware of that. And many of the people practitioner in this field, they also go for semi-kinematic design to overcome those problems. So for instance, last time I mentioned that if you look here, so ideally we start with the point contact, so ball on a flat, and what we can do is we just increase the area, the bearing area, so that the load capacity and the stresses developed at the point contact can be increased. So like the stresses will be reduced and the load bearing capacity will increase. At the same time, the stiffness will also increase. Similarly, if we have a two ball point contact, what we can do is this is equivalent to a line contact. And in that case, what we can do is we can spread to a wider area. And okay, we increase this area of contact. So these are called semi-kinematic because, okay, you started with the kinematic, the theoretical concept, and then you try to use averaging concept. So you try to average it out over a certain length so that you still get the benefit of kinematic design. So what people say, well, what the proponents of the kinematic design principles, what they say is one which has only a reasonable minimum of over constraint to overcome the limitations of a strictly kinematic design. So the idea here is if you go for kinematic design and you are a purist, many times you have a limitation. So as a practitioner, you are aware of those limitations, and then knowingly you try to just work around it. So that's why you say reasonable minimum over constraint. So you put so that it's manageable and still you can get the benefit of a kinematic design. So a very good example is like V and flat plane guideway. So if we go by kinematic design, it will be more like a V. So bottom will be V and flat. And on top, what you will have is you want to have a point contact here, right? Point contact here, and maybe point contact here, right? But you know, okay, it will have some limitation with respect to the stresses, and it may fail very easily. So then what you do is you extend. So you make it a flat. So this point will become a line contact here or over a smaller area on the V, and the V here, and this flat. So you will get the advantage of your 5-point contact, right? So okay, you can imagine that on the back side also you have a similar contact. And what you want to have is only this sliding motion. So this is there in most of the designs. So any older good lathe machine, if you see, they follow these principles. Even the many of these concepts are used in your ball bearings. So for instance, here is a ball in a V groove or a flat. So here the lower part, what you see here is you have a V, and then you have a ball, and top you again you have a V and the flat, right? But then okay, this is the ideal condition, but then you can very much use this V with the flats. And this you can use it as a roller system. So this is a semi-kinematic variant, you can call it, of the system. So many times you I also ask, okay, if you see certain designs, certain concepts, can you find a kinematic representation? What is the basis? What is the basis model? And how to analyze it? Because unless you are able to make it, unless you are able to convert into point and this flat contacts, so then only you'll be able to see what are the over constraints, what are the issues there in that design, right? So like in this example, if you see, you see one dumbbell and they are sitting on a two trihedral hollows. So these are like one and two. So these are two trihedral hollows. So it's like or a hole you call it. So I think in the last earlier lecture I mentioned that is just like this, right? So it's like a groove, but in this shape. And when you put a ball, a spherical ball, it makes contact, three contacts. So maybe like yeah, these dotted lines, there are 6-point contact. Maybe it's not done correctly. It should be somewhere here, right? Yeah. So this face, right? So it will be somewhere here. So one contact, two contact, and then three contact. Similarly, on this flat face, you have one contact. On this flat, you have another contact, and one you have this contact. So these three contacts will be on the three faces of the tetrahedron hole, right? And they pose three constants, right? Three constant on each side. So 3 plus 3. So how many 3 plus 3 contacts? So total 6 contacts. And that is equivalent to 6 constants. So ideally speaking, if it's an exactly constrained design, it should constrain all the 6 degrees of freedom, right? But here also you know that this axis, if you try to visualize, actually it can rotate. So what is saying 6 points of contact is yes, you still have one dot here, but 6 constants. So it's so ideally it should be only 6 minus 1. 6 minus 1, so 5 constants only. So it's a more. So 1 is more, right? So what is the degree of freedom is the rotation here. And what is the over constraint? Over constraint is also along the same line, and but that is the axial translation, axial degree of freedom required, right? So rotation is required here. I would say rotation that is desired, that is DOF, right? What about the translation? This is over constraint. Let's say over constraint. How? The way to look at it is, okay, suppose if there is a thermal expansion, what will happen? So this two trihedral hollows or tetrahedral hollows, if you talk about, if you want this dumbbell, this spindle to sit on top of that, you need exact dimensions, right? Otherwise, they can't make all the 6 tracks. It's not possible. So it has to be exact. Secondly, suppose if it makes contact and suppose you use some force, some preloading, so that it makes contact, deforms and make contact with all the 6. So suppose if there is any variation and suppose if there is any thermal change, so if there is any thermal gradient, thermal source there, there will be uh, it will expand, right, or contract. So because of that, there is a change in length. But if there is a change in length with respect to the base frame, which have which has these two hollows, and suppose it's like if there is a differential change, it cannot accommodate. So it means you cannot have those six constraints. And if you impose those six contacts by brute force or by preloading or by bolting it, it will develop internal stresses. So what would be the ideal case in this case? So just try to think about it. So I'm just making a trihedral. So there is a ball here, and this is suppose X I'm talking about. So of course 3-point contact here. So this dumbbell is constrained. What about this ball? So see, if there are three constraints here, right? In 3D space, three constraints. I need two constraints so that it can only spin. This is the desired of. So this should not, it should not go like this, right? So at this point, it should not move along this line, right? So 3 plus 4, and okay, of course, it cannot go out of the plane. So what? So for two contacts, so I need two contacts, 2C here, right? 2C is ball in a groove, V groove. Can give me that constant, right? So what will be the direction of the V? So if you look carefully, one is definitely, it should be sitting on the base frame. So of course the V can lie on the surface of the table. But what you want is, you don't want to have this motion. So it means the V, any V. So if you have a V along this line, this will not work, because then it can move, it can slide along this line, and it possesses constraint. So it means it's better to have this V. So this V is acceptable because then it can extend. So look at it, whether this is good enough or any V will work, except this perpendicular one. So look at it, which one is the better design, which one will give you the exact constraint design. This is for you to check. So similarly, like any ball bearing system, if you look at, what you realize that if you take simple this ball bearing, it allows rotation about X, right? If you take this, so I think this is the limitation, right? It's a saying rotation about X, but actually in principle it allows smaller rotation along Y and Z also. But okay, strictly speaking, suppose if you just want a rotation about X, you can go for ball bearing. But suppose if you want a rotation about X, Y, and Z also, and you want a ball bearing, it's a better to go for self-aligning or a spherical one. So you can also find this kind of ball bearings. So they will allow X, Y, and Z rotations also. But suppose if you want rotation about X and translation also, so it should be able to slide a little bit, then you go for roller one. So you can see this face. It's a floating, it's a straight edge. So if there is any movement, it can, and it can rotate, right? So these are you can say the manifestations of the degrees of freedom required. So you need to understand what is desired, what is your requirement, right? Whenever you design something, you should look at it in terms of degrees of freedom. What are the motions required in your design, right? I think one of the very like component I would say with respect to degrees of freedom is coupling. And people make a lot of mistake while designing or while connecting through coupling. So coupling in machine design, you have various kinds of, right? But ideally what you want, you have a drive motor or even a shaft, right? So, and then you have a spindle or load, right? Uh, Ideally what you want is the torque or the motion, right? This rotational motion from the this drive motor should get transmitted, right? So this torque, torque load or whatever, or the rotation, I think, or right. So in some cases you just want to like move by certain angular displacement and you want to follow this, right? In some cases you have a motor and you want to drive the load, right? This is the requirement, right? What about the other things? What about the other motion? If you are just talking about this XYZ motion, so suppose if I say call it X, okay, let's call it X, Y, and Z, right? These are the directions. So one by one, you can talk about it. Okay, if you are talking about coupling, what you want? Hmm? It should only transmit this rotation part along Y, right? If you want to achieve this, what you want is with respect to each other. So body 1 and 2, and they are connected through the member 3, which is called coupling. So the coupling allows connection between 1 and 2, and this one DOF you are talking about, that is the rotation about the longitudinal axis. That's the constraint. So it's one constraint, one constraint, right? What about the other five? Five are other DOFs. Why? Because what you want, that if there is any misalignment or any offset when you are connecting them, because this drive motor and this the load side, they can be mounted on different bearing. You are simply connecting through a coupling. So what happened, if you want that they should be perfectly matched, okay, of course, then in that case you want six constraints. And six constraints is like you have a flange coupling and you connect them through the boards, or you weld them. Many times people do that, but it's a really bad design, because what it asks for is complete alignment. So the two axes should be completely aligned. And if they are two separate modules, it's not possible. It's simply not possible because of manufacturing error or assembly errors. Hmm? So what you want, that even if there is any offset or any misalignment, it should readjust, but that coupling should provide one constraint, and which is this, which is about this direction, the rotation about this direction, completely constrained. So that's the requirement. So 5 DOF means if there is a little offset in X direction, it should flex, right? It should comply. So it means it should have a degrees of freedom. Along Z also is the same. Along Y, so suppose sometimes you want and sometimes you may not want. So it should be able to give that translation. Rotation also is because of some angularity. So suppose you have one axis here, and then suppose so this can be for the driving shaft, and the other could be like this also, right? So this is the load side. So suppose if you are putting a coupling here, what do you want? That this rotation should get transmitted. All others should be adjusted automatically. So same with the rotation. So rotation along X, rotation along Z, but rotation along Y should be constrained. So this is the coupling is one constraint. So this is the requirement. How to get it, right? So for instance, if you can see this case, so many times you like in design you do you use universal joints, right? Or you might have heard about all-done coupling. So there are a lot of designs, but try to visualize from this perspective, from degrees of freedom. So this is a flexure version. So here what you do, you take a single piece and then you cut it, reduce the section so that it can bend from here. And thus from there it can rotate. And that's why it's saying compliance direction. So it can rotate with respect to the other. So actually you are making a universal joint, right? So this is so it's more like if I look from this side, right? This side, one of the thing will look like this, and from the other side, okay. But what happens at this axis? So actually, what happens if you apply a moment, it can bend. So, so little flexibility is there because of this hinge design. Similarly, if you do in the other axis, it can bend in the other axis. So you can have two rotations. Of course, it's a limited. So it's a limited to degrees only in this case. So these two, so now you connect, you only get 2 degrees of freedom because of the two rotation. Here, this thickness is very substantial, so it will not deform. So it will not give you the translation degrees of freedom. But what happens? What happens if you reduce it? So now it's something like in 2D, it may look like this. And at top is connected, I would say. So you can imagine there is one hinge here, and this is, so this is also one hinge, but okay, maybe into a 2D it may be like that. And from here to here, but if this is now, this thickness is small. So this is like a beam. So if you have like this, something like this, and suppose connected, so this can flex also. So it can bend like this. So it provides you this translation also. So now it has 3 degrees of freedom. So 2 rotation and also this translation. Of course, these are limited. So what we are talking about, very small formations. What happens in this case? So these are like 2 universal joints. So 2 rotations here, 2 doff, and 2 doff here. So 4 constraints. Yes, so I think we'll continue. Okay. So what you saw that, okay, what are the semi kinematic variations, and like try to understand from degrees of freedom point of view, what are the basic design in various mechanical components or mechanical devices. I think we again try to recapitulate and try to see what happens. So we have already discussed these things, but maybe quickly go through it. So like we are talking about the table, and so very simple concept here, and many times in the machining shop or in the labs, older design, what you used to see is people used to clamp it very strong legs and then just clamp it here, right? And then you put a table on top of it. So what happens in this case? So anything here, any like sudden bump on it or like any change. So what happens? It will deform, and then it will get these bending moments will get transferred to top of the table because this table is rigidly connected to this leg. So there is a rigid connection here, either through bolts or through welding, right? It might be welded. So what happens? Anything there, it will get transmitted here, right? So it will get transmitted, and because of that, what will happen? It will deform. So what will happen to any object mounted here? So suppose you put an object here, it will also deform. And then suppose it's a very precise piece of equipment, the ring, the measurement, everything will get affected, right? So this is the problem, and this is because the bending moment is getting transferred. So if we follow the exact constraint design principle, what we want is this table should be constrained only with the 6 constraint, right? And any variation here, that should not get transferred to this space, right? So no transfer of bending moment. So suppose, so you can make it heavy, the bottom part, but the top where you want to put your sensitive equipment or anything you want to mount, but you don't want that it should get affected because of this variation on the floor, right? So what you do is you use through kinematic mount. So kinematic mount, so this piece is called kinematic mount. So 3 of them. So what they do is, so you see there is a cut. So each one will apply two constraint, and they are in parallel from base to the base frame to the plate. So 2 plus 2 plus 2, it's a 6 constraint. So usually if it's in connected, the connection is in parallel, the constraint get added. All the constraints should be added. 2 plus 2 plus 2, 6 constraints. So it will constrain all the 6 degrees of freedom. So individually they are constraining only 2 points. So what happens is equivalent to a ball in a V groove. So XY constraint, here again XY constraint, again here XY constraint. But 3 of them constrain total 6. And the good thing is any variation at the bottom will not get transferred there because it's getting transferred only through these points. So only the load, so only the translation will get transferred. But since it's a flexure, it will accommodate that change, and there will be no transfer of any bending moment on the top plate, and therefore it will not affect. So it will not get distorted. The top plate will not get distorted with respect to the bottom one. So that is the I think essence of the any kinematic design or kinematic mount. So another very good example, and like here with this example we can illustrate demonstrate or we can explain what is wrong if we don't follow the kinematic design principles, and what is the price we pay. This is a normal press, 4-column press, and what you see, there are 4 lights here, 4-column. So these are for guidance, right? And what you want, the middle one actually moves up and down. So if you just draw it here, what do you see? There is a frame and this thing moves up and down, and then maybe you have some piece here. So you use it, right? So there is a movement against each other, right? So suppose frame is fixed and this the thing which goes up and down. So what do you realize? That's only one DOF system. This is the degree of freedom you want. This should be able to translate. And by now, you might have realized that total degrees of freedom, if it's not constant, is 6. 1 DOF you need. So 6 minus 1 equal to 5 constraints. So these are the number of constraints you want, right? This is what you want, 5 constraints only, if you go by kinematic design principles, right? Now, what you see here is there are bushes here. So 1 bush here, 1, 2. So this is what you see here. So there are 4, and on the other side there are 4, right? So total 8 of them. So each one will have 1 bushing here, 1 bushing here, 1 bushing here, 1 bushing here, right? So on the other side you have, this side you have 1 and 1, right? So total 8 bushings. So what do you realize if you just, and they are all connected parallelly, right? So all 8 bushings trying to constrain this moving member, right? So putting constraints. So 8 times whatever is the constraint, right? N constraint. We don't know, right? So let's try to find what kind of constraints one bush will have. So suppose so this is a kind of cylindrical thing, and then you have a bushing, right? This is the bush, right? So with respect to each other, what it can do is it can translate, right? It can slide, but it can also rotate, right? It can also rotate. So there are 2 DOF, one translation and one rotation. So it means what it constraint is 4 constraint. So it cannot move in direction perpendicular to this axis, right? And then there are 2 rotations as well. So it cannot have. So it means how many constraints? So 8 times 4. 8 for the 32 constraint you are putting. 32 here. What is the requirement? The requirement is only 5C, right? So in this design, what you see is, in order it to function it well, what you want is it should move free along this direction, right? And in order to make it happen, there are few things, there are many things, but few things you can easily visualize, that all these 4 columns should be perfectly parallel, right? Parallelism of these guides. They should be parallel. Perfectly parallel, you say, okay, I can make it up to the 4 micron, 2 micron, 1 micron, yeah, whether you can go to the nano level, right? So going to a very precise level means a lot of cost. You need a lot of tooling. And obviously, no matter what you do, you cannot go beyond certain extent. Maybe of the order of micron you can achieve with a very good use of tooling, right? Secondly, the straightness. What is the straightness of these guides, right? So locally, if they are not straight and there is a variation, there is change in distance between the different points, right? That's the one thing. Now come to the slider part, which is moving up. They have a holes, right? These holes are there. How perfectly you can make those holes precisely at those points, right? Again, the cylindricity, circularity, the distance between them, right? These are all manufacturing tolerances. You cannot achieve beyond that. And if not, then what you have to do is you have to relax. You can't, because what happens if there is any, suppose if you get it right here, but if you don't get it right here, it will get jammed. It will not move. Or maybe at the time of assembly, at one point it's working fine, but at the other point it will get stuck. So we just did this calculation. So constraint 32 total. And so over constraint. So number of over constraint, if we talk about, equal to 32 minus 5, because 5 is requirement. So it will be 27 over constraint. So it means it's over constraint 27 times. So 27 times extra, right? Many times you say, okay, it increases the load bearing capacity, these are very big presses and all those things, right? But those are the design considerations. If you think that 5 will not work, it means you are not doing it properly. So you can still constrain 5 times, you can and get it run, and you can avoid this kind of. So what it says, much of the machining effort is intended to prevent positional over constraint being manifested in the design, because the way it's a design is a heavily constrained, and to take care of those over constraint, you have to make parts or components with a very high tolerances. And not only the parts, but even during the assembly, you have to take care of assembly procedure, you have to take care of the alignment, and that's the price you pay. So when you say that if you follow that exact constraint design principle, we have to use precise components, that's not exactly true. Actually, you use precise component when it's a over constraint design. But if it's not over constraint design, simple design can also work with the normal tolerances, normal components, and you can just do fine adjustment later. How? So just go conceptually. So suppose if you take this, the same problem, the press. So what you want to have is 5 constraints. So very simply, suppose if you start with this, so you assume that these are the point contacts. So these are some kind, assume that this graphite piece or something, and these are the guides, right? These are the guides, straight guides. So some simply you are doing like this. You are talking about this configuration, and this one you replace with this piece. So so it's a semi kinematic, I would say, because then you use a small surface instead of point contact. So now you assume that this is one contact. So there are 3 contacts. So top plate, you have 3 contacts, and the bottom plate, you have 2. So it's in parallel. So 3 plus 2, actually 5 constraint. Now try to visualize how it works, right? What you want is it should be able to move in this direction, right? That's possible, right? But the combination, so if you just take a section here and try to visualize, what you see here is if you try to rotate any of them, either orange or the blue one, with respect to each other, this theta constraint, right? So there will be a constraint line here, right? You can always start with a constraint line. This is very good tool. These are the constraint lines, right? So what happens? For theta, these two will be enough, right? This constraint line. Yes, here the assumption is the contacts are there. Huh? You have the 5 contacts made all the time. They are there. So you can say C1, C2, C1, C2, C3. These are the direction, C3. Same way you can have a constraint line, C4, C5, right? So, okay, theta is constraint. Same with X and Y also is a constraint, right? In a plane with the 3. At the bottom also you have, so you have this constraints here, right? But okay, I'm just making it red, but there are only 3 contacts at top. At the bottom you have 2. With these 2, what happens? If it tries to rotate this way, right? Entire thing, this thing will come in picture, right? So one pair, and same way out of the, so if it to rotate along this, so another pair will come into picture and they will cancel that motion. So essentially this 5 will be enough and it will constrain. Only allowed degree of freedom is this. This is the translation. So what you can do is now you can replace and you can put 4, 4, 8, 8 of them. But here what you do, 3, whatever you identified here, the 5, 3 plus 2, you use them as a reference with respect to the reference surface you have, right? 5. So other 3 you connect through springs, right? So which provides you the preloading. So you can make it adjustable also, so that you can change, right? These are the constraint direction, but by adjusting them you can preload, right? And then you can get the benefit and you can ensure that the contacts are made all the time. One thing is here, it's also talking about thermal center here. So center is the thermal center because as you extend the line, they intersect here and this point will not move. What is good about it is, suppose the blue one expands, it will simply slide along this direction and readjust it. So you don't have a problem here. There is no problem of binding or internal stresses develop and it will still work. So by careful design, you should be able to achieve. So when we talk about exact constraint design, what we are saying, what we are claiming for a high level of predictable behavior. Predictable means deterministic. Predictable behavior, deterministic behavior, and a minimum number of accurate dimensions. Minimum, you want to minimize because it adds to accurate dimensions, add to cost, right? So exact constraint design is a necessary condition. You have to follow the exact constraint design principles. Then only you can have a deterministic design and you can reduce cost by minimizing accurate dimensions. Let's take a break, I would say here. Let's just stop here. Uh, about over constraint and how it leads to problems, and as well as like overall manufacturing cost, right? So what we are also trying to claim that if you follow the exact constraint design principle, we should be able to achieve deterministic behavior. At the same time, we need minimum number of components with a very high tolerances, right? And that's the basis, that's the idea, and that's the point we are trying to advocate. And we explain through one example of a four-column brace. There are many examples we can see. One of the problem or one of the example could be your glass doors in many of the shops or in many of the offices. If you look carefully, you will see a lot of problems also there, and you find people struggling and maintaining, servicing them very frequently. So you can also try to visualize, and many times I ask question around them as well. Okay, whether you can have any kinematic design or exact constraint design, door design. So basic hinge. It's also one dot now, right? So column press is also one dot, and it's the translation. If you talk about glass door, it's a hinged, right? So you have one axis and it should rotate around it, right? So one rotational degree of freedom is desired. So how to put five constraint, right? So you can start with the constraint lines, and you can also uh, try to explain that how different dots, the other five dots, which should be constrained, and how you can realize it in practice, right? So that's the one part. Now let's continue. And what we need to understand is what are the elements, or you can say what are the components by which you can achieve these constraints, right? So, okay, for one DOF translation, we start with point contact. So we call ball with ball on a flat, and what we define is a constraint line. But in that example, we also discuss about a bar. So if we take a simple bar or a link, articulated along the constraint line, that that will impose one translation constraint. So in this case, if we have this pin, right, or call it a link, and articulating why we are saying is all the motions are possible, right? So this is the link we are talking about. So when we talk about this articulation, it means it can rotate. Only thing it will not do is the movement along the translation direction. This is constraint. So it can be a simple wire, also a steel wire. So if it's in tension, it can, right? So for one translation, you can always put a link, articulated link, and you can constrain one translation. Very simple. What about the rotation? Whether you have any building block. So for translation, you have this building block, right? You can start with this. For rotation, only rotation. But here what we are saying is which should constrain only the rotation. So suppose if you want to constrain the rotation of this orange part with this gray. So gray is your this thing. But you realize that you may not have any one link which can constrain the rotation only. It will always constrain other parts also. So suppose if you are just talking about these pairs, right? suppose you talk about these links, right? You can say, okay, this can also work, but essentially it's not, because what it does is it constrains this rotation, but it also constrains this translation. What we are interested is only in one. So whether we want to whether we can constrain the rotation only, and it's not possible through just one link or a pair of. What we have to do is we have to introduce a intermediate member, intermediate body. So essentially what it does is it tries to remove that constraint. This constraint is not desired, so you want to remove that constraint. So what happens if you consider this pair, right? So call it C1 and C2. With respect, so this blue, or what you call, I don't know, cyan, or I don't know the color name, but okay, it looks little green to me, greenish blue. So with respect to the gray part, the rotation as well as this translation is also constrained. This translation is constrained. Now, if you want to just constrain the rotation, what do you do? In the same plane, you put another pair which removes this translation. So if you arrange in perpendicular direction in the same plane, C3 and C4, actually it continues. They continue constraining this rotation, but it will remove this constraint, the translation constraint, what you have here. And then by this, you will be able to get one rotation only. So it's a composite structure. So rotation is complex, little bit complex. Of course, you can use them as a building block, and put in a such a way that, suppose if you need to remove the constraint in that direction, for translation you can use this thing. For rotation, you can use this pair, this entire piece, right? Fundamentally, you can do, but you can always get a better design where you have to do in combination, right? So then a little bit of creativity can help you, and some other methodology, right? So we'll look into that. Of course, one of the ways to constrain the translation is the point contact, this part. So ball on a flat. So if you have this and then this, you can always constrain, right? But what are the limitations? So what we are talking about, okay, till now we talk about the frictionless surfaces. But there are always some friction, right? There will be some friction, and because of that, it will also get locked. So if you have this F, correspondingly also you have mu FW, right? This along this direction, frictional force. So that is one thing. So suppose if you apply a force in a horizontal direction, it will limit the motion till you overcome the friction force. So you don't get an idea whether it's because of the friction or because of the constraint, right? That is one part. Second part is there will be always some deformation delta. So moment you have F, there will be some deformation delta along this direction. And this delta will be function of this F, right? So higher the preloading, higher will be the deformation. Another thing is the stresses. So there will be contact stresses developed, and there will be we'll also talk about the stiffness, because this can be always replaced with because when we talk about the dynamics, we all talk about this stiffness. So what is this stiffness, right? K, and or in the it's called C, right? So what is the stiffness? Can always replace with this some spring and then analyze it, right? So when we with the dynamics of any system, we talk about what is the stiffness and the damping. Even that we'll talk about the damping characteristic, right? So that is a problem, because all these things will be dependent on this app, this preloading. So what happens here? All these cases, I think you use Hertz principle, Hertz contact. So we talk about Hertzian contact, Hertzian contact. So any design book or mechanics of material book, if you look, you can get all the formulation. So these are for particular case, for a ball on a flat, and for steel ball and flat, right? So there are different material, different radius of curvature. So we'll talk about that in detail in other lectures. But here, just try to summarize that for a steel material, a steel ball, with a certain preload F and this radius of the ball. This, so that's why you see F and R. And what is important is here you get the E and new values of the material, and if you put them, okay, that's how you get these numbers. But what is important is this the dependence. So this stress, the contact stress, will be function of this loading and the radius, and to the power, right, F by R square to the power 1 by 3, the cube root, right? So this is not linear, right? Similarly, if you talk about the contact stiffness, so delta F by d delta, right? You will also get function and the cube root of R and F, right? So they are not only the function of this F, but they are also the function of this R. What is the size of the ball, right? So you need to know a lot of parameters, right? And what you understand, so if you have to use, so many times it can be used, and you can use this kind of designs as well, but then you should be aware that how this F and R affects the stiffness, and what will be the, so one of the critical parameter will be mu, so the friction locking. So what will be the friction force, what will be this delta, what will be this stiffness. So here we're talking about the stiffness and this preload. So what preload to use, right? What preload to use also, right? So one is with respect to load capacity. So load capacity you talk with respect to, so F will be basically what will be the load capacity, right, for given this arrangement, right? And this will be limited by the stresses. So what is stresses you will get? So these stresses, these will be the limitations. So in order to prevent failure, you have to talk about this. And this is for more about dynamic performance, the stiffness. So, and so what you realize that for different F, here, different loading, the curve for the stiffness is very different. There is a huge variation. Of course, it's non-linear. So suppose if you are talking about certain stiffnesses, so suppose if it's low stiffness, okay, you can talk about this number, right? But suppose if you are talking about high stiffness, then accordingly you have to talk about. So this is now design problem. So suppose if you want a stiffness of the order of by 3.6 to the power 5 Newton per millimeter, right? At the contact, this is the stiffness you are looking at. Then for this, so what is this? This radius for 1000. I think this is the radius. So this is the radius you have to talk about, and this is the F. So 1000 millimeter. So huge. This is a kind of thing you need, and this is the for 600 Newton preload. you will be able to achieve this, right? Uh, Even any less, you will have compromise. So you can always interpolate, right? So you need a lot of charts or certain, or you can use these formulations to get that, right? Generate and get it. What is the precaution here? What is the caution here is the stresses, kind of a stresses you develop in case of this point contact is very high. So even a steel ball of this diameter, maybe 20 millimeter diameter, dropping from 20 millimeter height can develop a stresses of 3000 Newton per millimeter square, right? So 3000, right? 10 to the power 6 Newton per millimeter square. Can imagine very high stresses and can be easily damaged. So even if you drop a ball on a hard surface, steel ball, uh, 20 millimeter height only, you can damage the ball. So uh, it has to handle very gently. Even if it's a steel, it can be damaged very easily. So that's the one thing. Other thing is because of the friction, it will get friction locked also. So suppose if you are using in this kind of surfaces ball in a groove, so suppose a spherical groove you have spherical contact area. So what is saying poor positional accuracy direction. How? Because what happens, mu will also not necessarily if you are putting a ball here and then pressing it, it will slide here. It may slide from here. So if you say here, it will slide, but it get free, get free, get locked here somewhere here. And why? Is because of this. So mu is always tan inverse. Here is alpha. You are talking about alpha. So it's a limited. So you talk about this case. So when you have an object and angle alpha, what happens? Right? So it's a 12 class physics, but you can always do it from here. So RH is this height. R is the RH is the radius of the hole. R is the radius of the ball, and mu square 2, and you should be able to get what is the uncertainty in delta Z. So please calculate it. It's a simple trigonometry, and you should be able to define this mu. So for given mu, what is the positional accuracy? What is the what you call limitations, right? So this is a kind of thing you're looking at. So it can stop anywhere in between, and that gives you error in z direction as well, and it's purely because of friction, mu. So many times when you are talking about this, you try to reduce this mu. Try to reduce as much as possible. So again, it's a derivation. So how to get this delta G, because initially say here, and this is your ideal location. This is the ideal location where you want to be, but then it may get stuck here, right? So try to find this value. It's the same as delta Z. So delta Z, so you try to find RH minus R, right? This length, right? Minus when it's already here, it get stuck here. And of course, mu is very small, so then this lambda, right? So cos alpha, yeah, cos alpha, and then u alpha will be equivalent to mu. And this is the relationship you can get. So of course, one translation, you can use this or you can use this, and this is the symbol you talk about, constraint. There are various other ways to constrain the translation, and this we will discuss later. So you can also have, so this is called folded leaf spring. So you can take a sheet metal and bend it sharp, and then connect it, and this will be your constraint direction along the bend. Or you can just take 3 strips. So here you bend it, right? Here you take 3 strips, 1, 2, 3, but then essentially it's 2 strips, and then they are like 1/2, 1/2 here, and this is 1, but arranged in the perpendicular direction, but along the same length. So along this length, it will constrain the translation. So please think about it. It's a very nice example. How to understand whether a folded sheet flexure or folded leaf spring will constrain one translation along the bending direction. So what will happen from here, what you see that this is the, so if you apply force F here, this will be constrained. So this not deform, this so call it 1 or 2. So part 2 will not deform because it's along the plane, but part 2 can bend, can get twisted. So that's why you show this, right? If you apply this force again, what happens along the plane of 2, it will not deform, but for A, it will bend. For this force, both will deform, both can bend. But what happens if you apply force which passes through the axis of the bend? So what happens in this case, along this direction, it can constrain the translation. So what is saying, only one location and direction, no high bending lines, no torsion. Okay. So just one example. Let me hope that it will run. It's a small video. I'm not sure whether you can see the video. I can see the video, but since it's not shared, I doubt. Let me close it first. Let me stop sharing and then share the screen. So I just want to show you this video. So I'll first share the entire screen so that you can. So you see this video. So what you see here is 2 leaf springs connected together, and then at the end you have this, so showing different motions. So the rotation, okay, it can rotate very easily, so it's a compliant direction again. Yeah, you can simply move, translate also. Twisting is possible. Now suppose if you, okay, the movement, but suppose you simply want to press along the line, you cannot. The stiffness is very high, and that's why it's not possible. The weight you see is mainly to provide balance. So I think very good example, and then actually this kind of setup we can also build and can demonstrate.